Okay, so continuing, we already defined what is VF and VR, and we have it right here. Now we're going to actually show the equations for velocity forward and velocity reverse. So velocity forward and velocity reverse can be shown as follows. VF equals to KF, little k, times the concentration of the reactant. So just a reminder that our reaction was Y goes to X. So Y is the reactant here. And V reverse is little kr times the concentration of the product, in this case X. Now the Kr and Kf, they're the rate constants for this reaction. Kf is the rate constant for the forward reaction, Kr is the rate constant for the reverse reaction. These equations were something you probably saw in General Chem, and this is for a first order reaction, meaning that the reaction is only dependent on the concentration of one reactant. For example, the forward reaction, Vf equals to Kf times Y, is dependent only on the concentration of the reactant, whereas Vr equals to Kr times the concentration of X is only dependent on the concentration of X. And the reason why most reactions in biology can be treated as first order and not second or third or etc. order reactions is because usually one of the reactants, if there is another reactant, is available in almost infinite amounts. For example, a hydrolysis reaction where we have AB plus H2O going to AOH plus HB. Well, H2O is the solvent, right? Because we're in an aqueous solution, so it's available almost in infinite amounts, so we don't put that into the equation and we just treat this as a pseudo first order reaction. And that the rate of the forward reaction is dependent on how much reactant you have, and the rate of the reverse reaction is dependent on how much product you have. So at equilibrium, we know that the rate of the forward reaction equals to the rate of the reverse reaction. And we had drawn this in the previous video where we said, okay, Y goes to X, right? At equilibrium, the forward reaction equals to the reverse reaction and its rate. This is at equilibrium, where delta G equals to 0. So what we have shown here is that, well, the rate of the forward reaction equals to the rate of the reverse reaction. And now what we're going to do is for VF and VR, we're just going to plug these equations in. Okay? And that's what we have done here. We have, for the forward reaction, Kf times the concentration of Y, and for the reverse reaction, we have Kr times the concentration of X. Now, a little bit of manipulation, doing a little algebra, and I'll just do it here just to show. I'm going to divide both sides by the concentration of Y. So I'm just going to write it here. Divide both sides by the concentration of Y. Right, and then I get Kf, the Y's cancel out on this side, and have Kr, concentration of X over concentration of Y. Remember, this is at equilibrium, everything, because the rate of the forward reaction will not equal to the rate of the reverse reaction otherwise. So we're at equilibrium. Now I'm going to divide both sides by Kr. So divide both sides by Kr. And I get Kf over Kr equals to X over Y. But we're at equilibrium. So the concentration of X over concentration of Y at equilibrium is just K, the equilibrium constant for the reaction. So now you see the relationship between thermodynamics and kinetics a little bit, right? The rate constants have a relationship with the equilibrium constant. So the rate constant for the forward reaction divided by the rate constant for the reverse reaction will equal to the equilibrium constant for the reaction. And since all these are constants, they're not going to change. These are fixed numbers, right? And that's what we have calculated and showed here. So remembering the equilibrium constant K is unique for a reaction, it easily follows that a catalyst, such as an enzyme, will need to increase both Kf and Kr, therefore increasing the rate of the forward and reverse reaction equally. So when we're looking at this equation up here, right? Actually, let me write it down right over here. So we have Vf equals to little k, the rate constant for the forward reaction, times the concentration of reactant. Right, in this case, it would be Y. And the reverse rate would be Kr times the concentration of product. Right? So we know that X and Y will change. As the reaction proceeds, the concentration of X and Y can sort of move around a little bit around a narrow range. So if an enzyme increases the rate of a reaction, it must do so by changing the Kf and the Kr. So when an enzyme gets involved, the Kf and the Kr will increase for that reaction. But since the equilibrium constant equals to Kf over Kr, then if I'm going to multiply Kf by a certain number, because now I have an enzyme involved, let's say the enzyme increases the forward reaction by 1,000-fold. Let us write this down. I put in an enzyme, and now Vf cat is 10 to the 3 times Vf, right? Okay, that's nice. Let's see what happens then. Well, Vf cat equals to 10 to the 3 K forward. I'm just plugging in the equation for V forward times the concentration of Y, right? Well, the concentration of Y has not changed. So I have increased the K forward by 10 to the 3. So now, if I just put in the equation for Vf cat, what will I have? Vf cat actually equals to, well, K forward catalyzed times concentration of Y equals to 10 to the 3 Kf times concentration of Y. Well, the Y's will cancel out because they're the same. Kf cat equals 10 to the 3 times the original rate constant for the forward reaction. So if I'm multiplying this by 10 to the 3, well, I can't change this number. The equilibrium constant is a constant. So I have to multiply the K reverse by the same amount so I don't change that number. So by multiplying the Kf by 10 to the 3 and multiplying the Kr by 10 to the 3, I'm essentially multiplying by 1. 10 to the 3 over 10 to the 3 is 1. So I retain my equilibrium constant for the reaction because an enzyme is not going to change the equilibrium constant for a reaction. Before I move on, I'm going to erase some of this stuff. Actually, I'm going to erase everything. And we'll push forward with the example we have here. So example, for the reaction Y goes to X, K equals to 10. This has been our example from the beginning, and we set K equals to 10 for this example. Assume Kf is 10 per second. Then by 7, and 7 is just this equation right here. Then by 7 we get, let's actually write that equation out. K equals to Kf over Kr. So we plug in K, which is 10. We plug in K forward, which is 10 per second, over Kr. Now what is Kr? Well, we multiply both sides by Kr, right? So we have 10 Kr equals to 10 per second, right? And then we divide both sides by 10. Kr equals 10 per second divided by 10. So my K reverse equals to 1 per second. And that's exactly what we calculated here. If an enzyme increases the rate of the forward reaction by 10 to the 5, then 8 was this right here, then 8 becomes 10 equals a 10 per second times 10 to the 5 over Kr cat. So this is just the same calculation we did before. We have our equation, K equals to Kf over Kr. Well, K is 10. We're saying that the enzyme increases the rate of the forward reaction by 10 to the 5. Okay, so we're increasing Vf cat equals to Vf, the normal Vf without the enzyme, times 10 to the 5. Right? Okay, so now what is Kf cat? Right? So we're going to calculate that. And we did that before, but we're going to do it again. So Vf equals to Kf cat times the concentration of Y, our reactant, and Vf equals to the normal Kf, the rate constant for the forward reaction without an enzyme, times the concentration of Y times 10 to the 5. Now the Y's cancel out because the concentration of Y is not different between the two sides. Kf cat equals to Kf, the rate constant for the forward reaction, without the enzyme, times 10 to the 5. Right? That's what I'm going to write here, since the enzyme increases the forward reaction by 10 to the 5, and we know Kf. Kf is given to us. Kf is right over here. Right here. Right? 10 per second. So we can actually stick that into our equation. So Kf cat equals to 10 per second times 10 to the 5. Right? So the K for this equation for K will equal to Kf cat over Kr cat. And we just figured out Kf cat, and we know K is 10, so 10 equals to Kf cat, which is right here. This is just going to be 10 to the 6 per second over Kr cat. And then we do the same way of solving, which is we multiply both sides by Kr cat, and then we divide by 10. So we get Kr cat equals to 10 to the 5 per second. And what is 10 to the 5 per second? 10 to the 5 per second is just 1 times 10 to the 5 per second, which is our original Kr times 10 to the 5. Because our original Kr was what? Our original Kr was 1 per second. Right? So the whole thing being done here, that is all of this. And I just to go back and look, this was our original rate constant for the reverse reaction right here, right? So if an enzyme increases the rate of the forward reaction by 10 to the 5, then 8 becomes the following, which we showed, and this gives us a Kr cat of 10 to the 5 per second. Okay, so we'll stop here, and we will continue the next video from this point. Thank you, guys.